We're going to have to do it inside, I guess. So, okay, welcome to class. My name is Joshua Vogelstein. Most students call me Jovo because they don't like saying Joshua, and I don't like saying Dr. Vogelstein because it confuses me. So you can call me Jovo or something like that. I'm teaching today and Friday. The topic is statistical connectomics. I haven't sent you any lecture notes or slides because I didn't make slides, and there aren't really notes other than I give this lecture sometimes. All of this content is more or less stuff that we and other people have been doing for the last several years, but it's really not written down yet in a textbook or in any publications. Presumably that will change if I ever write papers on this stuff, and eventually there would be course notes, but in the meantime, just, listen, I guess, and if you have questions, ask me. I'm happy to be interrupted. I know this stuff reasonably well, so it's kind of boring for me to say it, but it's more fun for me to talk to you guys about it. So please do interrupt if I say something confusing or stupid or whatever. Don't worry about asking stupid questions because I've asked them before and much stupider ones, so you're safe ground there. I wonder, do you guys have any questions about anything before I start? Has anyone seen me lecture on some stuff before? I know the answer is at least some of you. What did you see me do?
Stuff on big data.
Big data? Anybody else? You've seen me do stuff.
Yeah,
What,
big data.
what I do in front of you? Big data things?
Yeah.
Okay. So, is everybody comfortable? Can I get anybody anything? Glass of water? I guess you could get it yourself. Okay. So I do statistics of brain networks for the most part, and that involves lots of big data, it involves lots of brains, it involves lots of networks. I think it's the best thing in the world, and I encourage you guys to agree with me. Hopefully some of you will, and then we can do awesome stuff together at the end of these two lectures. I'm going to teach you some stuff that basically the only people in the world that know it are like me, a couple of my grad students, and some of my collaborators, and no one else. So you will be very well situated to do awesome things with this knowledge because you will have kind of a secret in that no one else has. And I think that'll be useful for you going forward. So most of you are juniors, is that right? Is anyone a senior? Yeah, why are you in this class? You didn't take it last year? Or you failed and you tried to take it again? Just to take it. Okay. Yeah, classes are hard. Okay, anyway, so you're junior, so you'll hear this now, and then next year, if this seems like the most exciting thing ever to you, which I imagine it will, then you can email me and we can do more stuff related to this. So, just by way of background, I'll tell you a little bit what motivates me to work on these problems. I come from a science background, like my father's a scientist, and so I grew up knowing about science. And he studies cancer, which turns out, cancer really sucks. It kills a whole bunch of people every year. It doesn't care if you're rich or poor or like where you're from, it still kills you eventually probably. So he's been working on cancer for a long time. And we're pretty competitive in my family, as you may imagine. And so it's, there's that things like, well, you're not curing cancer, right? Well, he is curing cancer. So it's hard to think of doing something that's more important than curing cancer. But, when I was in middle school, I thought about that a lot. Because it's like, how am I going to one-up my dad? It's kind of a big deal. And so it turns out, like, not everyone gets cancer, right? Like, a lot of people get cancer. It really sucks for them and their families. But a lot of people don't get cancer. But there is one thing that unifies all humans on Earth, and even the ones in space. Not only does it unify all the humans, it also unifies all animals. Vertebrates, invertebrates, land animals, air animals, water animals, dinosaurs. And so I wonder if you guys have any idea what that might be. What? Just yell it out.
Brain.
Yes, brains, right? Every animal has a brain. Every animal doesn't have skin, every animal doesn't have hearts, right? Like, do flies have hearts? I don't know, probably not, right? They're little. I don't think they have hearts. They don't really have blood exactly, so what would they do with the heart? The same with C. elegans, these little worms. The elegans are worms. There's like 1,000 cells, more or less. 302 of them are neurons. There's no heart. There's just a brain. And that's pretty much all you need. In fact, there's arguably single-cell organisms that kind of are a brain, which is a bit of a philosophical point. But the point is, every animal on Earth and anywhere else in the world, or the universe, or the multiverse, has a brain. So if we can figure out how brains work, and that would be cool, because that could be relevant to everybody, whether or not they get cancer. So that is a nice kind of one-up of my dad. But the other cool thing about brains is that sometimes they don't work the way that we want them to. Like, some people want to be happier, or they want to be able to attend to things longer, or they want to be smarter. And society has this kind of proclivity for labeling people and saying, oh, you feel this way a lot, therefore you have this disease, and you feel this way a lot, and therefore you're special in this other way. And it turns out these kind of psychiatric disorders and neurological disorders are hugely problematic for the world. So if you look at things like the World Health Organization, they evaluate the burden of disease, and there's lots of different classes of diseases. There's heart disease and lung disease and injuries and attacks and blah, blah, blah. It turns out neurological disorders are amongst the most burdensome and projected to be the most burdensome in the next 20 to 30 years. And the reason for that is that people that are suffering from these disorders live a really long time because they're often physically relatively well, but they don't work, and caring for them is really expensive because they often can't care for themselves. And so as it turns out, because these people have to quantify everything in terms of how expensive each disease is, it turns out if you have some of these psychiatric or neurological disorders, it gets really, really expensive for the world. And so lots of our, say, tax money and arguably future wars could depend on us being able to treat, and arguably even better would be address them before these come up. So that's one of my big motivations. So beating my dad probably is going to be a big deal eventually. And the other one is, anyone here heard of artificial intelligence? I figured you might have. And like deep learning, people know that term? Machine learning. So let's say Google is a company that does a bunch of artificial intelligence, right? And they've got supercomputers right now that consume about, I don't know, several megawatts of power that are getting pretty good at being able to tell whether this picture is of a cat or not. They still can't tell in a YouTube video if it's a cat or not, but if it's a picture, they're pretty good at cat or not. It turns out their supercomputers that can solve that very important problem of cat or not require about a megawatt of power and take the footprint of those buildings, or like, bigger than the footprint of this building, and many, many tons. Whereas human babies, I have a 15-month-old baby, he is really good at identifying cats instantly, and he only eats like a few hundred calories a day, right? And his whole body is like 20 pounds, and he's like this tall, right? And he's smarter, just in cat or not, the best supercomputer in the world, who's like about 1 million times more energetically costly and bigger and etc. Despite the fact that he can do all sorts of other awesome stuff. Like yesterday, he learned how to spin around in a circle and make himself dizzy and fall down, right? Google's supercomputer cannot do that. It's not clear whether it will ever do that. Whether that's intelligence or not, I'm not sure. But the point is, there's lots of things that human minds and even non-human minds can do that are super awesome that machines can't do yet. I and others believe that one of the main reasons that we can do that is because the brain has been very haphazardly evolved over the last, say, billion years or so to be able to store and process information incredibly efficiently and quickly, and in a way that's robust to certain kinds of adversarial attacks and stuff like that. So that is why I am motivated to study these things. And I realize lots of people have other motivations, but that's the background of that. So does anyone have any questions about my motivation? You're not going to be tested on it, but I think it's relevant. Okay, so that's why I study brains, but then I also study statistics, and I'm going to tell you about statistics of brains. So why do I study statistics? Well, it turns out, let's go back to the psychiatric disorder things. You can plot, this I've been looking at recently since I have a baby. This is like age, and this is, say, weight. Okay? And this curve is the growth chart. This happens to be the mean, and then often there's a median, and it looks like that. And then maybe there's a 95th percentile, it looks like that. Have you guys seen these growth charts? There's one for boys and there's another one for girls. They're slightly different. There's also one for height and weight. And so this thing, which you can print on a piece of paper and send to any doctor or nurse or a health practitioner around the world for about a penny, is like one of the most valuable pieces of paper anyone can have, because it turns out when you're a baby, if your weight is like way low or way high, it is often indicative that you're going to have a problem later. A pretty severe health problem. Like if you're way underweight, it may indicate that you're malnourished. That means that your brain might not be getting all the calories it needs to develop properly, and you're going to suffer because of that later. Same if your weight is too high, you may not be digesting food properly, and that can cause all sorts of other problems. And it's a similar thing if it's height, being too tall or too short at an early age, not just at any particular age, but if the growth of you is like this, that might be okay, but if it's like this, that's going to be problematic, or if it's like this, that looks problematic. So these trajectories of height and weight for babies are incredibly important, incredibly valuable. They're also incredibly simple, but you need to be able to compute, this is the mean weight at a given time. And also you need to be able to compute, say, the 75th percentile and the 95th percentile. Right, those are quantities that we compute to build this chart. So one of the main motivations and kind of new applications that we're working on is we want something like this for neurodevelopment. Right? So we want to be able to take kids, say you're born, and look at your brain and say, hey, everything's hunky-dory, go off and play. Or say, uh-oh, your brain is like screwed up a little bit, let's keep watching it. If it fixes itself in a few months, it's all good. If it's still screwed up in a few months, we can start early treatment, because it turns out that if you treat people really early for all sorts of psychiatric disorders, it can really mitigate the amount that they suffer and the amount of treatment that they need later. So we want to be able to build something like this for psychiatry. And as you've noted, I need to compute these things like a mean, 75th percentile, 95th percentile. That is statistics. I don't know, who took statistics? Which ones did you take? Like 3 something in AMS? Did anyone take 420 and 430? Okay, so all of you know something about statistics, and you know, everyone here knows what a mean is, and the 75th percentile. Okay, so that's all statistical stuff. And the reason that you kind of, well, I'll ask you, why do you trust when someone tells you the mean of something? Why do you trust that number? Or do you trust that number? Someone collected, say, the height of 10,000 babies that are a year old, and they tell you the mean. Do you trust the number? Are you raising your hand? Yeah? Yeah, so he said it's unbiased. Right, which means if there's a true mean, so x hat is our estimated mean, the expectation of it equals the expectation of the actual real data, of the population. This is a sample, right? So unbiased means the expectation of our mean is right, basically. That is a good thing, but some old dead dude had to prove it. Turns out we know it now because they taught it to you in 4 whatever, but an old dead dude had to prove it at some point. Is there any other reason you would believe it? Yeah?
I mean, I trust people's ability to accurately measure height.
Yeah, so the measurement, something about measurement accuracy. I'll just write measurement up here. Right, you trust their measurements, and then you trust their calculation of the mean. But why do you trust that they, I mean, this is some theory. There's a lot of theory that people have, right? People had the theory that communism was going to work. Didn't work out that great. So there's theory, and then we estimated things. But why do you trust the number? Like, they're going to give you a number. Why do you trust that? I agree that the theory matters and the measurement matters, but there's more to it. Just because there's theory and they measure the numbers right doesn't mean that this quantity they give you is trustworthy. Yeah?
You have reproducibility, so if someone says that their mean is this, then I can go out and get another 10,000 babies, and if I have a similar mean, then I can reproduce.
Yeah, so I would say that that comment is essentially about the variance. And so in other words, I have the expectation of this mean, but I also have the variance of this mean. And I know what the variance of this mean is, because some old dead dude proved it, is pretty small, basically. When n gets really big, the variance gets really small, and so it's a good estimator. What else? Anything else? Yeah?
Just building on the variance idea, like finding rate on the quantities that are too prone to outliers. So like you follow that very convenient.
Yeah, so the comment here is, it's a comment about robustness to outliers. As it turns out, the mean isn't quite a particularly robust estimator, but one can derive robust estimators such as the median or things like that. And since there's not very many outliers in height or weight, we don't need to worry about it that much. What about the fact that like millions and millions of people have calculated the means and like it pretty much gave them the answer that they thought it should? How do you guys feel about that? Fine? Don't care? Like, what if I gave you a new estimate of the mean? I didn't tell you how it worked, but I told you I proved that it's unbiased and it's robust and has small variance and that it's better. Would you just start using it? You could. You're in R or MATLAB. What do you guys program in? MATLAB? Really? Everyone in MATLAB these days here? Okay, we'll work on that later. But someone gives you a new, they just replace in MATLAB, you type mean. Turns out they rewrote the C function that MATLAB calls. It does a different thing. It doesn't do what you were all taught. But I told you, I proved that it does these things better. Do you trust it, or do you use MATLAB R 2016A instead? You revert? Can we take a vote? Who uses MATLAB R 2016A, which has the old way of doing the mean? And who uses 2019A pre-build, which uses this new way that I just proved is better, but you've never seen it and no one else has ever used it? You're going to use it?
I mean, assuming that it's within a reasonable range of what the previous estimate was.
Now you try it first before you start trusting it. Yeah. So, yeah, I agree with all that. You want, when you're building something like this, you want to be able to say a bunch of things about the estimators that you're using to say compute the mean and the variance and 75th percentile. You like a bunch of theoretical claims, and you like a bunch of people to have used it, and for it to kind of work out the way it wants, because lots of people prove things that work great, and in practice it works terrible. I can tell you because I read those papers and I try to run it. It's always a mess. So just because they prove things doesn't mean it's great. So with that, the reason that we do a bunch of actually foundational statistics is because I want to estimate things like the average connectome for 1-year-olds, and I want to be able to prove that it has all these nice properties, and I want to be able to demonstrate empirically that it has all these nice properties on real data, apply it to one data set, and then someone gives me another data set, I want to apply it again, I want to demonstrate that it gives me about the same answer, and all that stuff. And then once I trust these estimates, I can actually build this growth chart and send it to everybody in the world, and then they can check their kids and see that everybody is developing well. So is everyone clear on that? That's why I care about doing statistics right. Okay. Okay, so let's start with the mean just because it's fun. You guys said you know how to compute a mean. That's the mean of one kid. Okay, this is the network of one kid. This is baby 1. This is baby 2. Okay, this is, each node is a part of their brain. Each edge says that that part of their brain is connected. Like this could say that visual cortex is connected to motor cortex, for example. And this edge may say somatosensory cortex is connected to the amygdala, whatever. Okay, now I have 2 estimates of networks. I'm not telling you how I got them. Maybe I used MRI, maybe it was microscopy, whatever it was. I got these. Okay, you guys know how to compute the mean. What's the answer? Oh, that was a hit. Mean. This is we're in MATLAB, right? So just put in these 2 things. Mean. Right? When I need to build this growth chart up there, I need a mean function on my connectomes. Because I'm estimating networks. Connectome means network of the brain. Someone gave me them. I'm assuming that if the network goes awry, that other things are going to go awry. Then they gave me 2 estimates of the network. Then we know how to compute mean, we said earlier. Pretty sure you guys all laughed at me when I asked you if you know how to compute the mean. Well, how do I do it? Yeah?
Locations of the vertices like correspond to the same vertices?
That's a great question. So I intentionally didn't tell you the answer to that. So let's say this is, we'll number them. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. And your question, if I understand correctly, is vertex 1 over here the same as vertex 1 over here or not? What do you think? Does anyone have a guess? Yes? Either answer is totally fine with me. I know how to do it either way. Let's say they're all the same. So this is vertex 1. Let's just say we're in visual cortex. So this is V1, V2, V3, V4, V5. I don't think there's really a V5, but that's okay. V1, V2, V3, V4, V5. All visual cortex. Okay? Now how do we compute the mean? Yeah? Okay, if I understand the suggestion, you're saying build, this is baby 1 matrix, this is baby 2 matrix, 1, 2, 3, 4, 5, 1, 2, 3, 4, 5, and say baby 1 is connected to 2, 2 is connected to 4, 1 is connected to 5, 3 is connected to 4, basically like that, and do the same thing for baby 2, and then add them. Yeah, okay, add them. And then there's going to be some zeros here, and then some 1s, and then some 2s. And then divide by n. How do you guys feel about that? It's a suggestion. I'm a big fan of concrete suggestions. This is one. Who wants to use this as their estimate of the mean? You said it. You don't even want to do it? Okay, some of you don't. Some of you do. Who doesn't want to use this? Why not?
Because you can't have, like, say, 1/2 of a connection.
It's a good point. You can't have 1/2 of a connection. So let's make it simpler. Let's say we have a coin, and we're just flipping it. Heads and tails, heads, 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 tails, tails, tails. What's the mean? This is a coin flip. You guys knew about coin flips before you walked in here. What's the mean? Is it like this character? Just throw out, say whatever you feel like is the mean. It's okay. All the answers are fine with me. Yeah?
Is it just 1/2 times expected value of each point plus 1/2?
So you're saying the mean is going to be something like 0.8, basically. If you say the t's are 1s and these are 0s, it's whatever, just take the average. Is that what you're saying?
Yeah.
Who likes that answer? Who doesn't like that answer? What do you want it to be?
It's like the same thing, because if you have a mean of like 0.5, like while that like represents something, it still like isn't shown there. Like this head is 0 and tail is 1, but 0.5 like represents the middle between the two, but it doesn't represent a specific thing.
I agree that you've identified a problem, but I would ask you, what should the mean be if it's not that? Yeah. Yeah, it's not that obvious what the right answer is, even for heads and tails. I think both of them are fine. So one answer is you take the average. The other answer could be you just say the mode. Most of them are t's, so we'll just say it's t. And then most of the time we'll be right. Won't always be right. And then there's other more complicated things that we could do. Even that totally trivially simple example, we don't know what to do. In here, it's obviously way more complicated because there's not just one coin flip, there's many coin flips. So computing the mean is not that straightforward, but more or less, this idea I think is basically the best one we've had so far. That's what lots of people do. You write it down. This is called an adjacency matrix. Adjacency matrix. You write down an adjacency matrix where you say, so if A is our adjacency matrix, element I, j equals 1 if and only if there's a connection from I to j. And so it's 0 otherwise. Can you guys see this? This color's kind of weird. It's green on a black. Okay. Anyway, that's the adjacency matrix representation. Lots of people represent things that way. And then you can compute the average that way, and it's a fine thing. So now we have our average. So going back to, should I use this thing? This is cool. It's like before they invented the internet, you had to use this stick. So now we have 1 point here, right? Because we measured a whole bunch of brains, and then we got an average. Okay, do you guys want to figure out how to do the 75th percentile? All right. We're going to need more than 2, so let's say we got more than 2. Let's go with 4. There's another one, and there's another one. I don't feel like drawing it. Okay, now we got 4 brains. What's the 75th percentile brain network? How are we going to get it? The second highest brain? How do you sort brains? I like sorting brains, but I don't know how. I know how to sort numbers, right? It's like 1, 2, 3. 3 is bigger than 2. It's cool. But like, what if I give you 2 vectors or 2 brain networks? I want to sort them, but yeah.
What you're trying to measure, what if you wanted to measure like number of connections, somehow like sum all the elements or something, but then it depends on what you're trying to represent.
I agree with that. It depends on what you're trying to represent. So the way I like to do things is try to make everything as simple as possible and figure out if I can do it in that setting. So let's go back to the coin flips. What's the 75th percentile of the coin flips? What do you want the answer to be? No, it's still not that obvious, right? Like somehow even less obvious than the mean, which was confusing and we disagreed about what the right answer was. Okay, so let's do something simpler. Let's say, let's say we just got numbers on the real line. Where's the 75th percentile? 3/4 of the way in. It's a good answer. So, so this is 0.5. This is 0.75. This is 0.25. So where's 3/4 of the way in? Is it here?
Starting from here.
Let's say I'm going just from 0 to 1. Thou shalt not pass. Of this data, where's 3/4 of the way in on this data? Yeah? Thou shalt pass. So what you do if you want to compute the 75th percentile is you essentially, let's say there are 100 samples we got here. We find the 75th largest one, and that's the 75th percentile. Right? Because the data happens to not be uniformly distributed between 0 and 1. If it was all uniformly distributed, then the answer would be there. But we're going to find the 75th percentile largest one if the numbers are between 0 and 1. Does that make sense to everybody? Is that obvious to you? Does it feel like it's the 75th percentile? Should feel 75th percentile-y. Okay. So let's go back to these brain networks. Now we know how to do it if the numbers were between 0 and 1. What should we do here? That's pretty fun. Any ideas? Yep.
Different weights into each end, and then divide it by the number of total possible numbers.
You want to give weights. So that's a great idea, and that's what we thought we should do also, because I couldn't figure out what to do without the weights. But I could figure out what to do with the weights because I knew what to do here. So let's see if I can get this one back. Jesus. Okay. So this was an adjacency matrix, and we said Aij equals 1 if and only if I is connected to j. But we could say these don't have to be 1s. This is a 2, this is an 8, this is pi, this is e, this is negative 24. Right? Who says they have to be 0 or 1? In fact, the data are rarely actually 0 and 1s. Like if you're flipping coins, it's 0 and 1. But often if someone tells you the data are binary, what they mean is the data were not at all binary, and then they decide to threshold it and make it binary because it was going to be easier. Well, turns out it's not necessarily easier when things are binary. In fact, I have no idea how to compute the 75th percentile when things are binary. But if they just give me the weights, then I say, this might be true, but there's a weight matrix, which equals, say, connection strength. Okay, and someone estimated the connection strength. I'm not concerned about how or who they did it. I'm just going to assume, for the purposes of this, that their measurement error is small. Right, so now we're going to trust these connection strengths, and then we're going to get, this is one baby's brain network, and this is another baby's, and there's 4 of them. And then what are we going to do? Yeah? For each element of this matrix, we just take all the data, sort it, find the 75th percentile biggest one, and that's the answer. How do you guys feel about that? To start, does anyone have a different idea? Yeah, I don't really either. I think that's a great idea. So, okay. Now we did that, and we got 75th percentile for that age group. That's cool. So, you guys feel like you could probably do the 95th percentile and the 5th percentile without me at this point, right? So like if there was a test hypothetically and I gave you like 2 or 3 brains and I asked you to say, find the 33 percentile brain, you could do it now? If anyone, the answer is no, let me know now so I can figure out what you're missing. Everybody happy with that? This class is 8 hours, right? No, it ends at 2:30? to 10? Okay. So we only have 10 minutes left. Okay, so that's the start. I didn't tell you about any of the statistical properties of that, but it turns out we have proven a bunch of things, not about the 75th percentile, that's too hard, but about the mean. We can compute means of brain networks, and we can do it that way. We actually do have a better way of doing it under certain assumptions that require making several assumptions about the data. So in the remaining time, I want to motivate for you why we make assumptions about the data, because it'll help explain the assumptions that we made to make our estimates better. So to do that, I just want to start very simply. Let's say we have a brain, and there's a brain network, and there's 3 nodes, and say there's 2 edges. So how many possible networks are there with just 3 nodes? 6? You just yell the answer. 6? One guess is 6. What are they? This is one of them. Let's draw all 6. I can draw 6 things. 3, 4, 5. Okay, what's this one look like? That's this one has 2 lines from top to bottom. What's this one? An L. Okay. What's this one? Backwards L. Okay. What's this one?
1 line.
1 line. What's this one? No lines. What's this one? Another 1 line. Oh wait, done? Okay. What's the next one? The other 1 line. Anything else? All lines. Okay, how many was that? 1, 2, 3, 4, 5, 6, 7, 8. 8. Okay, you guys want to do it when there's 4 nodes instead of 6? Counting is hard. I tell you now, I can count to 4 and 8, no problem. But does anyone inferred the rule for how one might determine, say, if I gave you a network and it had n nodes or n vertices, how many possible connection networks there could be? 2 to the n is a guess. Does anybody have a much better guess? A much bigger guess? You're actually very, very close, 2 to the n. You're close in theory, but in practice it's about 0 relative to the right answer. Yeah. 2 to the n, choose 2. That's fancy. So, okay, let's think it through. Everything is binary, right? We all know how to do binary. So let's say there's only one binary thing, then the possible answers are 0 and 1. Right, that's 2. That's great. Now let's say you flip 2 coins. What are the possible answers? 0, 0, 0, 1, 1, 0, 1, 1. 4 choices. Okay? Now if you do 3, you get to add either a 0 to each of these, or you can add a 1 to each of these. So you multiply it by 2 again. Right? There's 4, etc. So if in general, if you have a binary sequence of like 1s and 0s, then there's, what's the answer? How many possible sequences? Somebody say something. 2 to the n? N squared? 2n? These are all possible. N over 2? Does anyone want to vote? If there's only 1 bit, it's 2. If there's 2 of them, it's 4. If there's 3 of them, it's 8. If there's 4 of them, it's 16. 2
to the n.
2 to the n. Okay. Great. Okay. Now, we have, say, 3 nodes. 1, 2, 3, 1, 2, 3. So we're going to think about this as a binary sequence because each of these elements in this matrix can be a 0 or a 1. So there's 3 nodes. How many potential edges are there? Anybody? Potential edges. There could be one here, or 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 here. 3 squared. So if there's n nodes, there's n squared possible edges. You guys with me? Yeah? You have a question? I have implicitly assumed that there is a direction to the edges, which means there could be an edge here and not here, or vice versa. Yeah, that's a good question. Okay, so if there's n nodes, there's n squared potential edges, right? It's just any node can potentially make an edge with any other node, right? So for each node, there's n potential edges, and then the next node, there's another n potential edges. So there's n of those nodes. Each one has n options. That's n squared options. So there's n squared things that can be 0 or 1. Yeah? That's a great question. If we say n choose 2, we kind of secretly, implicitly assumed maybe not. But I'm assuming yes because it makes the math easier for me. And hopefully for you too. So yeah, there can be an edge from 1 to 1. It's totally allowable. And there could be one from 2 to 1, but not from 1 to 2. All of those things are okay. Okay, so you guys all with me? And that n squared is the total number of potential edges if there's n nodes. Okay, so how many potential networks are there if there's n nodes? Previous guess, well, one was 2 to the n, the other was n to choose 2. So you can think of this, you can just vectorize this. It's just 1, 2, 3, 4, 5, 6, 7, 8, 9. 1 to 9. 0, 1, there's 9 of them. How many possible sequences, binary sequences of 9 bits are there? Yeah, so the answer is 2 to the n squared possible networks if you have n nodes. Okay? So let's just plot 2 to the n squared. I'm going to plot n versus total number of different networks. And I'm going to say it goes like, no, I'll say it goes, well, I can draw a line. So here's 10, 20, 30. What do you think this number is at 30? This number. I mean, it's 2 to the 30 squared, right? How big is 2 to the 30 squared? Let's try to do it intuitively. Are there more, say, hairs on your head than 2 to the 30 squared? Are there more atoms in the universe than 2 to the 30 squared? Are there more possible chess games than 2 to the 30 squared? Yeah, so 2 to the 30 squared is about 10 to the 300. Ten to 300 is really fucking big. Right? Yeah, way bigger than number of everything else. So, and that's if you only had 30 nodes. Do you guys know how many nodes are in your brain? I say each neuron is a node. That'll be a homework question that you won't get graded on because time's running out. But next time we'll start with how many nodes are in your brain. If anyone figures the answer out, you start counting. By Friday, you should know the answer. Anyway, the point is there's a lot of potential networks, and so we're not going to observe all of them. And therefore, we're going to use statistics to try to estimate things from the sample that we observe about the population in terms of, say, growth rates and trajectories and things like that. So, okay, I will see everybody on Friday.